Okay, so now we'll finish up section 518 and work example number 5.6. 518 again is dynamic braking and mechanical time constant. And we'll work this problem and hopefully it'll make some of these uh, ideas about dynamic braking a little more clear to put some actual numbers. So to get us ready, I've written down a couple of equations that we're going to need and made this to where we can look at the dynamic braking curve as we put these values in here. And one thing I meant to point out to you in part one of this is this constant. And, one thing that is, I guess it's sort of a reward, at some point, because, when you get to this point, you're given these equations and they have these constants and these values. And luckily, we don't have to derive them, do we? They're thrown over the wall and we just get to use them and do our explorations without having to go through the other part. And we get to leave that to the physics class and the math classes. So this 131.5 is equal to 30 divided by pi squared divided by the log base e of 2. Okay? Now, I don't know about you, but I think the derivation of that would be pretty involved, and so I'm glad that's just handed to us and we get to run with it. So example 5.6 says that we have a 225 kilowatt, which is approximately 300 horsepower motor. That's a big motor, isn't it? It's rated at 250 volts. The rated speed is 1280 RPMs. It says it has windage, friction, and iron losses of 8 kilowatts. Okay, so he's given us these losses, so and those would be hard to determine, but for the purpose of this problem, he's just given us those numbers so that we can work through this. The motor, this 300 horsepower motor, is connected to a large flywheel, and it has a moment of inertia between the armature and the flywheel. The total moment of inertia, the J number, is 177 kilogram meter squared. And then the motor itself is connected to a 210 volt DC source. Now, you say, well, what's this if we're given that? Well, this is the motor rating, okay? This is name tag stuff. So it doesn't necessarily mean that that is what's connected to it. It's what you're capable of connecting to it. So it says that in this particular situation that we're going to work with, it's connected to a 210 volt source, and it says that its speed is 1280 RPMs just before the armature is switched to the braking resistor, which has a value of 0.2 ohms. You go like, wow, that's almost no resistance. But remember, we're looking at some very large currents. So even though the resistance is very small, it has to handle a lot of current, and it also has to be able to handle that amount of current to be able to dissipate the heat that's generated in it. Okay, so those are our conditions for this problem. And he says, I want to know what the mechanical time constant is of the braking system. Okay, so we're going to have to use 5.9 to do that. And then he says, what's the time for the motor speed to drop to 20 RPMs, and then the time for the speed to drop to 20 RPMs if the only braking force is that due to the losses that are given to us here. Okay, so first things first, let's see what we have. I have a J number, right? I have a J number here, and I'm going to know the speed, okay? And I can determine what the power is, right? I can determine what the power is because it's given to me here. So this really looks like something that we should be able to manage. Let's see if I've got the room here to just work this on what we've got going here. So, you know, we're given the voltage and we're given the resistance. Now we have power is equal to V squared R, one of the basic power formulas. So if we were trying to determine what this particular value would be, we would say the power is equal to 210 volts applied, because we have that here, that value squared. And I'm going to divide that large number by a very small number of 0.2. And when I do that, I get the initial power delivered to this resistor is 220,500 watts. Wow, that's a lot, isn't it? That's a lot that this resistor is having to manage. Now, once I have that value, I can plug that into this equation for the time constant that I need, because I have the 177. I'm going to lose units here because I'm kind of maxed out for time. Times the speed squared, 1280. Okay. Then I have a constant of 131.5. And then I have the power in, which is 220,500 watts. Okay. If I calculate that out, do the math, I don't know if it exactly comes out to this, but he says that that value comes out to be 10 seconds. Okay. So that gives us part A of this problem. Pretty much, you know, other than having to calculate what the power is, it was pretty much of a just plug into this 5-9 formula and go from there. Okay, so the second part, it says, what is the time, or how's he phrase this? Let me hold back here. What is the time for the motor speed to drop to 20 RPMs? Okay, now he does this. I like this, and what I'll do too is I'll come back and set up a formula to do this. But you know, if the time constant, the half time constant is 10 seconds, and so initially we're at 1280, right? So at time 0 we're at 1280. After one of these, we're going to be half that, 640. After another one of these, we'll be half that, or 320. Another 10 seconds, we're at 160. Another at 80. Another at 40. So after 60 seconds, we're at 20 RPMs. Okay, so we can see that that value comes in at this point here. And again, I'll show you. We'll model a formula where you can just place the time in there. But I think I like that. I mean, I like this this way because you know we're getting a good feel for what's going on with that. I like that. So anyway, part C of this has us try to make the same determination without the braking resistor. You know, the only portion of this that we're looking at is basically the windage, friction, and friction losses. You know, in other words, we're just letting it coast to a stop. Okay, and so in that case, you know, if I plug this in here, I have to get a new half time constant. It comes out to be 276 seconds. Okay, so in the other problem, it took us 1, 2, 3, 4, 5, 6 time constants to reach 20. We can know, or we could deduce that it would take the same, it's proportional. So, you know, it's going to act basically the same way, follow the same curve. And, you know, just keeping the mathematics at a minimum here, that means that we would need 6 of these new time constants, which would come out to be 1,656 seconds, and that is about 28 minutes. So with the braking resistor, we ended up, you know, with it took a minute, and then without it, it took 28 minutes. So the mechanical time constant is 28 times the original. Now, in theory, the motor that's dynamically braked never comes to a stop, you know, because, I mean, if you look at this curve, you know, it never really hits the 0 point. But, you know, if you're thinking about the windage and friction losses, you know, we realize that, you know, it will come to a stop. And just like we looked at with inductors and capacitors, we'll think of it being completely stopped after 5 of these half time constants. We're going to consider that. Okay. And then there's one other equation, which is equation 510, that says if the motor is plugged, the stopping time has a definite value. And that value is given to us by T sub S, and it is equal to 2 times T sub 0. And so we're going to utilize that in the next problem. So let me stop here and we'll make a part 3 to this. All right, so stopping that now.